And one set is vertex. Vertex set, we can it's a non-empty, any non-empty set. So B is any non-empty set. And there is another set. That we find this is all still in all those books. But this E, there's something here which E is corresponding to. So the E is actually just giving the names to those edges of arcs. But what are the edges of arcs look like? They either have one end or two ends. Sometimes ordered, sometimes not. So it is actually a marking from this to this. I have introduced that in order to do this. Now this gives what? This gives every edge would be an arrow. What happens to the edges which edges are or loops which are not arrows? We forget the order. Using the forgetting function, we forget the order, or we probably regard that as arrows going both ways. Arrows going both ways. It goes A, B, and B. This is in that Cartesian product. Then we replace this by just AB. Right? And now we don't restrict set B. We don't restrict set E. That is we need to just say that this is a marking. Isn't that right? Any graph X is a marking from E to V cross B. If you introduce other conditions, then it will forget. If you want to have simple undirected graph, you replace the right hand side by just V choose 2. Let me rewrite another line. This is simple undirected. This is all directives. This is simple undirected. Simple because we're choosing subsets of all the two. We're not choosing simple. And this marking, of course, the two edges coming up on the same one, in which case we require that X must be injective. So if X is injective, then it is simple undirected. Injective marking. Simple undirected. If B is finite, then it is finite graph. X is finite graph. If B is not finite, then it is infinite graph. So one thing we will have to clarify further, this second line here, if X from B to B choose 2 is injective, then it's simple. It's called simple. Not only so, any injective marking can be considered as an embedding, right? In this case, X is an embedding, inclusion. Inclusion is also called embedding. If it is an embedding, then where we recover what? This. This is E. Sorry, E. This E is now a binary relation because it's now a subset. Right? So we have every binary relation. Binary relation is a simple graph. It doesn't matter if B is infinite or finite. So every binary relation on B is an example of a simple graph. How much we have included now. Now let us write down how this marking looks like for these. So this will do these two and that one. So you can actually write down this marking in each case. In that we need to have a give name. We're not labeling the graphs. The graph labeling study, I'm not too much interested. Don't study graph labeling. If you listen to me, you don't get the job. We are giving names. We're not labeling them. 1, 2, 3, 4, 5. A, B, B, C, D, E. So the set D is equal to 1, 2, 3, 4, 5. Set E is equal to A, B, C, D, E. And the mapping X is equal to A is mapped to 1, 2. Let me just write 1, 2, it's not 12. Instead of curly bracket 1, comma 2, we just write 1, 2. And we're assuming here that AB is equal to BA. Because of unlimited. B is mapped to 2, 3. C is mapped to 2, 4. E is mapped to 3, 5. E is mapped to 4, 5. You see? You can write down the mapping. This is the mapping, the final mapping is done in this two-row array. Pre-image, image. And it's injected. That one, we're going to write down the mapping only, and by first giving names to the two types, two sets. So we have again 5, and that's 1, 2, 3, 4, 5. And we have to give names. This is E1, E2, E3, E4, E5, E6, E7, E8, E9. So X is equal to E1, E2, E3, E4, E5, E6, E7, E8, E9. And we give the image under each element. Just usually finite markings are notational finite marking. E1 is 1, 2. So now we clearly put it in the set. And so E1 is, its end is 1 and 2, it doesn't matter which way. E2 is 1, 5 order. So easy. E3 is 2, 3. E4 is 3, 4 curly. E5 is 3, 4 order. E6 is 5, 5. One of the diagonal elements. E7 is 4, 5. E8 is 5, 4. E9 is 4, 4. I'm a good accountant. Now I have to do the count. So we don't need, you see here we also have another major comment. Maybe if you ask graph theorists, they will tell you that graph theory is a new concept since 1936. 1936 was the first graph theory was written by Dennis Koenig. And the first graph theory paper was done by Euler in 1736. They would tell you that graph theory is a new mathematical concept. This is is not, because we only use sets and mappings. These were well-known mathematical concepts before that time. So graph theory is not new. Let me tell you this case. The concept of a graph is not a new concept. See it more clearly. Let me not forget what I was trying to say.
So, Professor, if it is mapping, then we can say that in pre-image we have edges, and in image we have those vertices which is connected by that specific edge. Like in pre-image we have E1 and as an edge, and in the image of E1 we have those two vertices 1 and 2 that are connected by that specific edge E1.
This
Right?
set.
Yes.
This set is the end of E1. E1 is the set to consist of two vertices.
Right.
And E2 is an arrow from 1 to 5. E3 is an arrow from 2 to 3. Arrow is round. Round bracket means order matters. Curly bracket means order doesn't matter. Only thing we need is we don't repeat inside. And very rigorous, because we are not offending any mathematical concepts. We're using only sets and mappings to define a graph. Now, only thing is that this codomain here consists of not only ordered pairs, some ordered pairs, and also some singletons or unordered pairs, two sets of two elements or one element. You can write it like that, and it's a good accountant. The accountant should do this kind of job. This is one thing. Another thing is, yes, many, when I was in conferences in USA and so on, UK, many people even explicitly say that this graphs we study has nothing to do with graph of a function. Do you think it's true or false? Graph of a function of one variable, let us say, the one real valued function of one real variable. It's a graph, isn't it? Let me consider this. Any real valued function, complex variable, no problem, but one variable. Many variables also the same thing. Real valued, let us just consider real valued function of a real variable. You just give me the two sets. The set V, what is the set V?
Subset of the real number.
Yes, set V is the real numbers. So actually domain of the, yes. Set V is domain. What is E?
No.
Let us just have a look. Let us just have a look at.
Also subset.
It is any subset of R square, the ordered pairs x and f of x.
Yes. F and you're right.
Yeah.
Let us consider this. So this point
Yeah.
is ordered pair of x and f, x squared.
Yeah.
This ordered pair real number is in V cross V. What is E? E is this point on the plane. This point on the plane is the edge which is mapped to this ordered pair. Almost identity mapping, we're looking at. Almost identity mapping. So the point, let me write it in word this time. X, fx plus h is mapped to ordered pair of real numbers this is just a teasing because these have nothing to do with us. Just teasing whether that statement is true or false. X and X. When we look at this, we see it as an ordered pair of real numbers. When we look at that, we see it as a point. That's what we're doing, isn't it? We are looking at this as a point. Isn't it a point? That's the coordinate of a point. Coordinate of a point. This is an ordered pair of real numbers. We are mapping that point to this ordered pair. So this explains that functions are graphs.
So Professor, in second graph we have for E6. So there is a self loop from 5 to 5.
This one.
Yes.
E6.
On E6 we have a self loop, right? From 5 to 5 again.
Yes. E6 is a ordered pair 5-5.
So it should be only 5.
No, it's ordered pair. So
Order ladders.
when we are forgetting orders, we take out the diagonal. Otherwise, we don't need to take out. It's still binary relation. D is actually a special case of binary relation. So no problem. And how about this one? Let us label each edge with this right hand. So this one is E1, this one is E2, this one is E3, this one is E0, this one is E-1, this one is E-2, this one is E-3. So x is equal to dot dot dot. This is a count rule, so we can list it. E3 is mapped to negative curly plus set, -4, -3. E2 is E-3, E-2 is mapped to -3, -2. You see that if you have a proper nice concept, you can actually become a good accountant. You can straight away write down and you can put it into Python. You can type it into Python and work it. So the E-1 is negative to -1. E0 is -1, 0, and so on. This, I have to say that this is, first of all, I have to give myself good feeling that this is a good concept and nicely done. And any other opinion? Now I'm going to say very contradictory. This is not good enough. It is not good enough, and we're not going to correct ourselves, even if it is not good enough. It is good enough if it is appropriate. Then, in mathematics, if some concept is really defined nicely, then we have at least 3 advantages that you have to really know in mathematics. If a concept is defined appropriately, not using the verbal description in those 20 books, if a concept is defined appropriately, should be, this is true in every field of mathematics, then the definition gives us at least 3 advantages. And we're going to demonstrate. I written down into 3 advantages. And we're going to demonstrate that now. Only if that is done, then we see the advantage of this definition. Where is my definition? It's gone. So let me write it somewhere high, and so that we don't forget. So, okay. V is non-negative. X, E, to V cross V. That is our definition for, at least for directed graphs. Finite or infinite, doesn't matter. It must give us 3 major advantages. I'm going to demonstrate that now. So let me copy my own definition on top of this board. I'm very proud of this definition, but nobody said anything when it was in archive for 20 years, because 2005 to now is 30 years. Nobody said anything, only this and all that. This internet is really so we rewrite this on top of this board. You will see that how advantageous this becomes. So this can be rewritten as E arrow to B cross 0. And X is here. X is a mapping.
Yes.
So when you have a mapping with arrow from domain to codomain, now it's very obvious that we can generalize this domain, we can generalize this codomain. Let us generalize the domain first. One of the generalizations, not all, one of the generalizations, instead of taking one set, we take a finitely many sets. Right? So let us say it's E1 to E2 to S. The right side we're not going to touch. From each of these you have R. X1, X2, nothing, X. What do we have now? We can give a name, very good, simple name to this, using two words. If you have one equation, you have an equation. If you have three linear equations, you have a system of equations. So this is a graph system. Graph system. Graph system, but it's not good enough, because what is this actually saying? It says that you are going to have a collection of different sets, H sets, on the same vertex set. Right? You have a same vertex set which is infinite or finite, doesn't matter, a collection of SCH sets on it. So this is not new. Let us now try generalizing the head of the R. He is there alone. And X is still there. One thing you can think about is E, you write it R, right? Yes. The R. R-fold Cartesian product. What does this give us? Let us assume for the moment that X is injected. We get what? It's a very well-known concept. It's R-array relation on V. It's R-array relation, the order matters. The elements inside can be repeated. Order matters. You can't permute and get the same one. This is an R-array relation. X and R-array relation on V. We are always inside this in mathematics. R-array relation on V, and now you can slightly more generalize it. Instead of taking just one R, we take a union of R1 to M. See how beautifully it is giving us so easy major new concepts and much more complicated concepts and all those set system books and hypergraphs we call it. Union R going from 1 to M, the R. This gives you relational system. X is a relational system. More general than the last relational system, which was between two monographs. Nothing is done yet about this. current relational systems, current concept. And the reference is inside the slide, so which is going to be uploaded. So we don't need to use English and Knauer and Klabzar and Neshetri, all famous. They wrote some books which contain the concept of a relational system, but this is more general because in the relational system, this side is actually V choose R union. V choose R union is not all, it's a subset, taking subsets. But here it is ordered R tuple for R going from 1 to n. So this is more or less directed relational system. And in this case, we said it already is Ex from E to this is called set system. Also called hypergraph. I don't like the second word. This is better. Because most solid work on this kind of mathematical objects have been done by Hungarian school, and Hungarian school always call it set system, starting from Abdus to now. And this hypergraph is a French school. So hypergraph is an extreme special case of our second generalization. The first generalization didn't give us anything new, which is just a graph system. Second generalization gives us a new concept, which is called relational system. And this is our relational system. This is the relation. And this one is set system. Great things are going on. And set system so far studied by Hungarian school is V is finite. So here we don't restrict V is finite. Just have a look at this concept. Topological space. You collect all the subsets which we call open sets into this side. So set system covers topological space, topology, matroid, lots of mathematics. They are all set systems. We are just collecting sets, certain sets, and put there and call it something.
Are they topologically same?
Topological space is a set system. Only that B's ground set is not necessarily finite. And we didn't say it's finite. So topology is a special case of this. Only that the sets you're putting there satisfies 3 more conditions. Empty set, we put it there. Oh, we need to start with 0 here. Empty set, the whole set, you put it there, and then the others these have to satisfy the intersection and union condition. And you are in this category. Here R can be 0, because R0 gives you nothing is chosen, so it's an empty set. Or if you keep it 1, you just put empty set separately, like all agreement, by agreement. So now, first, this is very abstract now. First generalization didn't give us new concept. Second generalization gave us at least 3 new concepts. Oh, 2 new concepts. This one is well known in discrete mathematics. This one is more general than the current set system, and this one is set system comes out as a generalization naturally from our definition, and not only so, V can be any set. The set system studied are usually finite set systems. Now, putting this on both sides, generalize there into finite sets and there into this. Then you have a relational system. The real general relational system. So let me just write it as if we generalize on tail and head of the arrow. Both we have general sets. Nothing is done here. It's completely new. Yes. I'm glad that this paper is now published. I didn't submit, but I always, it was in the archive for 20 years. This journal, which is an unknown journal, wanted the paper from me, and I have some ready papers, and this is one of them. Not much new results in it, but new concepts and some related basic results. So I gave them the topic. It's there online. I'm glad that this comes to the concept of a graph. Before we go further, I would like to mention that every concept in graph theory is separately written in many monographs. One monograph district is called directed graphs, finite. One monograph of district is about infinite undirected graph. And there are 5-10 textbooks and monographs on simple undirected finite graphs. So the graph theory has many monographs and textbooks. What was I trying to say? There is something we need to say here. Before we proceed next. I'm too old. Still young? Thank you, but I'm too old. Oh yes, what I was trying to say is not written here, and I suddenly thought of. Every concept in graph theory, in all of those graph theory, but let us say basic concepts. Can all be presented by means of arrow diagrams. That's what I'm going to emphasize. And it makes it a proper mathematical subject instead of ambiguous verbal presentation. Every basic concept in graph theory can be made exact by means of arrow diagrams. Arrow diagrams. This Professor McLean would be very happy because when he was alive, I was with him for half a year when I was doing PhD. Professor McLean was the author of Saunders McLean was the author of Categories for the Working Mathematician. You read that book. That book is very good. Categories for the Working Mathematicians. In the yellow series, Saunders McLean is the author. He actually didn't examine my PhD thesis, but read through it and gave me very interesting comments. Well, by that time, he asked that, can any of these things you are dealing with be done categorically? And then now I'm happy to, he's dead now, he's dead in 2005. Otherwise I would have emailed, everything can be in graph theory can be done with arrow diagrams, which means categorically. So for example, subgraph, let me mention a few. Subgraph can be done with arrow diagram. Induced subgraph can be done with arrow diagram. Path circuits can be done with arrow diagram. You just have an arrow with some commutative diagram or arrow with two ends. Now let me show you just one of them, complete graphs. Let us consider only finite graph this time, so that you are familiar with this the finite. Finite means its number of elements is a fixed natural number. We call it n. Then a bijective mapping. From E to B cross B choose 2 is called the complete graph. Complete graph of order n. It's obvious and denoted K sub n. So it has n vertices and n choose 2 are there and E2 that is bijective. So every n choose 2 H sub n. Similarly, you can define complete set systems. Complete set systems, because in set systems we don't include empty set. So complete set system is goes from 1. If B is still finite with n elements in it, then you are summing the binomial coefficients n choose 1 to n choose n. So if n choose 0 is included, then it is 2 to the n.
Yeah.
So 2 to the n minus 1. It has so many edges, it's bijective. So you can define it using such an arrow. This is an arrow diagram, isn't it? And then we need to define morphisms of graphs, and many of which are not well studied by graph theorists. So we are going to define morphisms of graphs. And we'll give you some examples. And our graphs are, it can be finite, it can be infinite, it can be directed, it can be undirected, it can be mixed. So when we say graphs here, we are talking about any graph defined by that arrow. We are not talking about finite graphs or undirected graphs. So morphism, let the x and y be graphs, because we're now using mapping x and y. Oh, before this, we need to notice that if we're talking of only simple graphs, we defined it earlier. E to V cross V, or we choose 2. If this x is injective, and it is the same as binary relation in this case. It is same as graph in that, simple graph in that case. So if a graph is simple and directed, then we introduce a new condition, which is this A plus B and B plus A are both there. We can either assume that, or A, B equal to, we denote this, again with being lazy, we denote this by that, and then we say that this is equal to BA. This is saying that it's undirected, this extra condition. We're not saying that this is commutative, because this is not a multiplication. This is a abbreviation of that. So if these are all understood, then we probably assume that we have a simple graph, simple undirected graph, not necessarily finite. So for that special case, we're going to define morphisms. So now we declare now that simple undirected not necessarily finite. This is already quite wide. Finite. It could be And in our case, in this mini course, mostly it's infinite graph where we are concerned. So we can write an edges xy. Edge. This means that the edge is written as xy. Please remind me of time.
Yeah, so.
Huh? So we have to start from morphism on Monday. Written as xy. We'll start from morphism on Monday. Questions and comments, please. I think you have been actively involved. I'm very happy because you should get it as your own. Don't leave it here. Even if this is not the last time we will lecture. Sorry. It implies that I might be dying tomorrow. For old people, it's not good to say dying or something.
Any question?
Yes.
In the upcoming lectures, we relate with the metric space, graphically with the metric space.
Yes. Yes. Because we're going to consider my metric space questions mostly on locally finite graphs. So this has to be done, and this is more or less new, this whole lecture. Thank you.
Sir, one question. My question is that you are saying both of authors are using the formal definition of graph in graph theory, which started from edges and vertices.
Yeah, it's
But
a
not
verbal
mention the
description.
mappings which you are saying today.
Yeah, verbal description, not giving you precise mathematical terms. They actually acknowledge that. the authors. This one. This one. This one. R-I. R-I. It's the binary is 2-I. Kernel is 3-I.
3, 4, 5.
Yes. R-I means it's an ordered arc. Each element is an ordered arc. Array is called. This one? This one? This is R-array relations. Because it's R whole Cartesian product of D. And if you take R going from 1 to n, you have all the arrays from 1 to n. So this is an ordered system.